Hello everyone, this is the senior design presentation of Group 18. Our project is the Rain Energy Harvester. Let us meet the members of the team.
Hello, my name is Evan Main.
Hello, my name is Carlos Molina.
My name is Alexander Rutherford.
And my name is Ryan Bacon.
The main concept of our project is to design a device that will be connected to a single gutter of a home and use the rainwater to generate power using a hydroelectric turbine and motor. While the turbine is rotating, the energy generated will be used to power a small external device like an LED light. This device can act as a supplemental source of renewable energy for large office buildings, shopping malls, and even small residences. For this project, we wanted to create a sustainable solution for energy generation while contributing to the preservation of the environment. And of course, take advantage of a natural source of energy that is currently not utilized. The goals of this project are that the device will be capable of generating energy through rainfall. The energy generated will then be used to power an external device while displaying the data about the energy generated. The specific objectives include to convert mechanical energy to electrical energy using a Pelton turbine and a stepper motor, use the energy generated to power an external device, use oak wood material with a water-resistant sealant and plexiglass material for the turbine and electrical casings to prevent water damage and also for demonstration purposes, and use sensors to gather the data to display on the LCD screens. Now let's see the engineering specifications of this project. The three specifications that we're going to demo are turbine speed, turbine efficiency, and the output power generated for the external device. These three specifications will be calculated from the data gathered from the sensors and will be displayed on the LCD screen. We're expecting that the temperature inside of this device will stay in the range between 5 to 35 degrees Celsius, which will keep the water from becoming frozen and the electronic components from getting damaged. The generation rate refers to the minimum power that will be generated by the motor over time, while the turbine is active under active operating conditions. We're expecting water flow rates to be between 2 gallons per minute up to 6 gallons per minute, and the dimensions of this project is expected to be less than 1.5 by 1.5 by 2.35 meters. The major hardware components for this project include the turbine, the microcontroller, the motor, voltage regulators, battery, LCD screen, battery, voltage and current sensors, power switches, and buttons. And now we'll go over each of these components.
The main types of hydroelectric turbines that were considered were the Turgo and Pelton turbines, as these types were best suited for the waterhead levels and flow rates that we expected. Ultimately, the Pelton turbine type was chosen due to its slightly higher efficiency ratings and lower flow rate requirements. Several Pelton turbines were compared, and we selected the model that had the highest number of adjustable paddles with the highest runner diameter. We knew that we could reduce the runner size later if it was too large, and we knew that we could adjust or even replace the paddles if the stock paddles underperformed. When determining what microcontroller unit to use, we used the following factors to make our selection. The I2C peripherals would share the same 2 data pins, while the SPI peripheral would need 4 to 5 data pins. This means that very few data pins are actually needed for the project, so a lower pin count was sought. This project is far more hardware focused and only basic functions and calculations will be handled by the MCU. So this means that the bit count, the memory, and the clock frequency are less important as a result. The MCU and its peripherals will be powered by an external battery, so the operating voltage, power consumption, and low power mode options that were available were also considered. Group members were already familiar with and owned both the Arduino Uno and the MSP430 models, so those were considered immediately. Ultimately, we decided that the Arduino Uno and the ATmega 328P microchip would be the best fit for our project, as the advantages of the other models were either not important enough to justify getting it or were too cost prohibitive.
The motor for the project is responsible for converting mechanical energy to electrical energy when the turbine is rotating. For this purpose, the criteria for the types of motors were chosen for a motor being used as a generator. The criteria included cost, shaft smoothness, complication, and efficiency. The shaft smoothness and efficiency were important for the usability of the motor because of the estimated 2 gallons per minute water input to the system. The low input would mean less force available to spin the motor and a low amount of energy able to convert to electrical. Hence, the shaft being easy to spin and conversion efficiency being high was important. Each motor had a different complication when it came to integrating the motor to the system, and less complicated motors were sought for if other criteria were not being sacrificed. Ultimately, the stepper motor was chosen for the design of the project. The stepper motor was on par on efficiency compared to most of the other motors, while being inexpensive, easy to rotate, and easy to integrate to the design. The only complication for the stepper motor was the need to change the output to AC to DC by full bridge rectifiers. Two variations of the NEMA 17 motor, as well as the NEMA 23 motors, were compared when selecting the part for the project. The goal when comparing the motors was to select the motor that can output the most suitable voltage and current values for the small-scale devices. While any of the motors would work for the design, we determined that the NEMA 17 17ME15 was the best for the project. The motor had the most steps compared to the other motors, and the max voltage was relatively high at 73 volts, resulting in a potential increase in voltage and current output than the other motors. With the potential to increase output and the cost being on the lower end of the $1699, the NEMA 17 17ME15 stepper motor was selected for the project. The voltage regulators will be used to step down the voltage from the battery to microcontroller and to step down the output voltage of the motor. There were two types of voltage regulators researched: the switching regulators and the linear regulators. The switching regulators can step down, step up, or do both, and was rated with high efficiency and heat resistance. The linear regulators can only step down voltages, but is simpler to design and less expensive. While efficiency is a drawback, the heat resistance can be solved by adding a heatsink onto the regulator. With the project only requiring the regulator to step down voltage and the reduced cost and complexity, the linear regulator was chosen. 3 different linear voltage regulators were compared, with criteria being cost, voltage input, voltage output, and current output, and dropout voltage. The LM317 was determined to be the most adequate for the project. The allowed voltage input and output of the LM317 was the most versatile, making this regulator suitable for both the motor output and the step down to the microcontroller. The current output was on the lower end of the regulators, and the dropout voltage was on the higher end, but since the current is not expected to be high, and the microcontroller recommended voltage can still be reached with the dropout value, these drawbacks did not necessarily affect the project performance. The battery will be used as the power supply for the microcontroller. The battery chemistry and size were compared to pick the most suitable battery for the design. The chemistry was chosen to be alkaline, and the size was chosen to be 9 volts. Alkaline was chosen because it was commonly sold around the store, and its capacity was high without being too expensive. Knowing that power supply was only going to be on when the user wanted the display status, sacrificing some capacity to save costs was well worth it. The 9 volt size was chosen because the battery in the project will run at recommended levels to the microcontroller. The 9 volt battery size allows of only needing one cell to reach recommended levels, than the alternative of needing multiple cells if other battery sizes were chosen, making the product design simpler and cleaner with the 9 volt size. 3 different batteries were compared when deciding the one to use for the design. The MN1604 was chosen to be the battery of the design. The capacity and duration were similar, and the cost may appear to be higher than the other batteries. The MN1604 battery was available in store, which avoided the delivery fee, therefore was chosen.
For this project, we consider different types of displays and panels, which include the twisted pneumatic displays, in-panel switching panels, vertical alignment panels, thin-film transistor displays, and OLED displays. Our screen needs to be able to display text and a graph with high resolution and refresh rates, while providing the same display performance across different viewing angles. Response times refer to the time it takes the screen to change from one color to another, which determines how fast the screen can update. The TFT and OLED displays were great options for our project. However, TFT display on average consume significantly less power over time than OLED displays. OLED displays with significant screen size also are more expensive than TFT displays with the same screen size. Ultimately, we chose the TFT screen as our display. When making our screen selection, we also considered some OLED displays that can be used in our project. However, we ultimately decided to use the bigger screen size with higher resolution of the Adafruit TFT ILI 9341. This display has a resolution of 320 by 240 pixels, which is more than enough to display the data with high image quality. It uses SPI as its interface, which is what we were aiming for. This is because SPI have a higher data transmission speed between the MCU to the display than the I2C interface. We needed this higher refresh rate to ensure that the graph of power over time was going to update accurately and in real time. For the voltage and current sensor, we considered different methods that accurately measure these two volt values, and we selected the method that was the most appropriate for our project. The sensors that use the Hall effect principle, or the induction method, mainly added an additional layer of complexity for our specific application. These two methods would have required additional components to guarantee accurate readings, such as a current clamp. We decided to use the shunt-based method. Even though it is an invasive method for measuring, this drawback can be mitigated by using low resistance shunts, which are resistors with very low resistance. For the sensor selection, we consider sensors that only read voltage and current, as well as some alternatives that can measure both. Since our objective is to accurately measure the power generated, and we need to measure the power from the motor and from the outlet for the external device, we selected the INA226 sensor that can measure voltage, current, and power with high accuracy. This sensor can measure voltage from 0 to 36 volts and current from 0.5 milliamps to 50 amps with 16 bits of resolution. We're also aiming for a sensor that will use I2C interface because we needed two readings, which meant to have two peripheral devices. Since this sensor uses I2C, then we can simplify the number of connections for both sensors.
Here is our hardware diagram. First, water flows down through the piping, out through a jet nozzle at its base, into the buckets of the Pelton turbine, and out through the bottom of the turbine chamber. The turbine will drive the motor through mechanical connections that will be described later, and the AC signal generated will be converted to DC using two Wien bridges. This signal will be measured by the first shunt sensor. The signal will pass then through a voltage regulator and will be measured by the second sensor at the outlet of the system. A regulator 9-volt battery will be used to power the microcontroller, the sensors, and the LCD screen. The shunt sensors had address pins on them that were soldered together to determine each sensor's hex address. The 4-wire SPI option was chosen over the 8-bit parallel option, as the improved speed offered by the 8-bit option was not necessary and not significant enough for use in this project. The ATmega 328P has dual inline packaging, which allows us to use a socket that the MCU can be inserted into instead of directly soldering the MCU onto the PCB board. This gives us more freedom when choosing how to program the MCU and allows for easy replacement and testing of this component. Here are the major mechanical components in our project. These parts will be used together to connect the turbine to the motor. Here's our software diagram. First, the sensors in the LCD pins are configured. Then measurements are taken using the first sensor, and then the unit conversions and calculations using these measurements are performed. The program then branches off depending on what mode the prototype is currently set to, and this can be changed by the user at any time by pressing the LCD's toggle button. Mode 1 is used for displaying the measured values on the LCD screen in text form. Then the current flowing through the second sensor is used to determine if the outlet is being used. Next, text labels and units are displayed on the screen. And finally, values measured using both sensors are displayed on the screen. These values refresh every second. Mode 2 is designed to display to the user the power generated by the turbine using a line graph. The y-axis is power in watts, and the x-axis represents time in seconds. First, both axes are printed onto the screen, then the power measured by the first sensor is displayed each second. After 30 seconds, the graph is cleared and the process restarts. For the IDE, we considered the Arduino IDE, Code Composer Studio, and Visual Code Studio. The Arduino IDE was chosen due to its compatibility with our MCU, group members' familiarity with it, the large amount of available support, and the numerous GitHub libraries available in its library manager. Python and C++ were the two languages that were really considered for use in this project. Ultimately, C++ was chosen over Python due to group members' lack of experience with Python and the greater low-level control and memory optimization options afforded by C++. Some of the libraries that we are calling are listed below. The image on the left shows the text mode and the image on the right shows the graph mode. The shunt voltage and current _2 values are only present for testing and will not be used in the final version. The toggle button will be placed to the right of the LCD screen and will allow the user to change between modes. The outlet and two switches will be located beneath the LCD screen. One will turn the outlet on or off, and the other one will be used to control the power to the prototype.
Okay, so here we've got our overall PCB schematic. It consists of 6 parts, but the 2 sensors as well as the switches present aren't going to be present on the actual PCB. They will be external. So here we've got a full bridge rectifier with 2 bridges in series in order to convert the AC current to the DC, as well as a test point named IN plus T. Here we've got our voltage and current sensor number 1. This will measure the voltage and current output of the rectifier. The IN plus acts as the input while the IN minus is the output. Also, VBus is connected to IN minus as well. Here's our second voltage and current sensor, which measures the output of our output regulator. We also have a switch connected so we can control control when we want our output to actually be leaving the circuit. So here's our output regulator. The purpose of this is to reduce our voltage that we'll get from our generator to 5 volts. So for that, we use the configuration of a 240 ohm resistor and a 720 ohm resistor. Then we have our supply voltage regulator here, which will reduce a 9-volt battery down to 5 volts. We've also got a switch in order to turn on our peripherals. And this will be the circuits used to power our peripherals. This is our MCU schematic, which has a crystal named Q1 connected to the left to make sure the clock runs properly. Otherwise, we have our connections for our LCD in the bottom right, connections for our sensors in the top right, and then our FTDI connections in the top left, as well as an LED in the bottom left to make sure that the board is operational. Here we've got our board layout. you can see that all the switches, sensors, and LCD screen aren't present here because they'll be external. But we added pinholes so that we can connect them later on. In terms of our project progress plan, we plan on ordering our PCB by February 5th, and in the meantime working on our physical parts of the project, such as connecting the turbine to the motor using a shaft, a flange, as well as bearings. And we plan on having everything complete by March 4th. Here's the work distributions for every member. And here's our budget. So in total right now, we plan on spending $372.41. But we had to estimate for our mechanical parts because we're not exactly sure how much those will cost as of right now. So the current challenges we're facing mostly is in the mechanical design of our project because none of us have much experience with mechanical design. So creating the connections between the turbine and motor are proving to be more challenging than we first thought, but we're getting close to the end. And we also had some issues in FTDI testing where the adapter was not working properly. So our backup method in case this doesn't work is to just add a USB outlet. But we're confident we can get this working. And then of course the budget, we're still not sure about how much our mechanical parts will cost. But overall we're doing well right now. Thank you for listening. Have a nice day.